Record. Okay, so that was the last slide. I think that was the last slide or somewhere thereabouts that we finished last time. We're just going to quickly finish up. That was the SAN, System Area Network or Storage Area Network. And we went over that. Now, where's my... Yeah, that's better. Can I go here? Now, VPN. VPN is something that, well, it is quite popular idea. It used to be reserved pretty much mostly for corporate type of use. Basically, if there's a big chain of stores, let's say, I don't think that thing needs any large. Okay, any large. I'm not going to mention any names because any large department store chain would be on something that's called VPN. VPN, instead of running wires from one building to another, if the company owns multiple buildings, and there are certain companies that own a lot of buildings, and if everything, all the transactions, all the data traffic has to be harnessed at the same spot at the same time, then a VPN is the most practical solution for the data traffic. Instead of running wires from one building to another, then that would be just so unpractical and pretty much impossible to accomplish. What we have is those stores would log on to a reserved space on the internet that nobody has access to but that company only. And in this case, any kind of a transaction, you go to the cash register with a piece of chewing gum and you scan that through and the transaction goes through. Immediately that thing goes into the larger database through something that's called VPN, which stands for Virtual Private Network. The internet is already has that infrastructure laid all over the world. So why not just tap into it, reserve some space on it for ourselves, and instead of running wires, physical wires to connect those stores, we could just use something that's called a bandwidth of the internet to connect all those stores, and have this whole thing operate in the same way as if it were, well, a LAN, local area network, that will be contained to one building. So almost no difference when it comes to that. Now, sometimes you can see that so that will be the store kind of a thing here. That's just another visual for the same thing. You can view that once you download this thing. Now, just another example of VPN usage. This is the map of the world, and of course, somebody pick up the phone. Okay. I'm sorry. Okay. There you go. Somebody picked up the phone. All right. So this is the map of the world with different continents marked on it. And let's say we have a company that would just Control L here, bring it to the full screen. Let's say we have a company that owns multiple buildings and they are spread all over the world. If those log in to the same VPN, virtual private network, which will be purchased by the company who owns, the corporation who owns all those buildings, then all those facilities around the world would act, as far as data traffic, they would act almost the same way as a local area network would. Right? That's the beauty of VPN. Now, if you want to if one of the PCs wants to communicate with one of the PCs in the same building, which basically is next door, the same room, or the next room next door, in the same hallway, maybe, there will be no difference between data communication, and if that same PC would try to communicate with another PC that is in a different continent, let's say, for example, right? Also, that is very practical when using something that's called VoIP, Voice over IP, which is the telephone system that instead of using POTS lines, POTS stands for plain old telephone service, which is what we have known the telephone service to be as up till, well, last few years, using that the POTS basically uses direct wiring connection, one way or another. So instead of that, those phones are plugged into the network, local area network in each building, and that local area network can log on to the VPN, virtual private network. And again, there will be no difference if somebody picks up the phone and tries to call the cubicle right next to it, and or if that same person was trying to call another person that sits somewhere in a different continent, it would be just the same. Just dial the extension number, and the whole thing works as one common pseudo local area network, which will be on VPN. There will be no difference between two phones calling here and two phones calling here. No long distance charges, just an extension, dial the extension number, and then you're talking. Now, when it comes to using VoIP, the cost of maintaining the phone service is about 1/3 that would cost you if you were using the POTS service, not to mention the long distance charges if you want to, that would be applied if different continents would be called. And the quality of the conversation is much higher. So a lot of companies are switching to VoIP systems, and VoIP, when it's a new company being established, then of course it's almost no question there's going to be a VoIP system installed through VPN. Yeah, some companies would dish out a little bit of money up front, but then the cost of maintaining that comes back pretty quick. Now there's some little bit different details, because companies who do provide the VoIP service, they do also find a way to charge for this, charge for that, charge for the other thing. So instead of charging per phone line, so the phone lines are cheaper because they're called SIP lines. SIP stands for Session Initiation Protocol. So it's basically like connecting through internet. If you are calling up a website on a browser, you're establishing a session between your PC and the server on which that website is residing at that moment. So it's establishing sessions. So session initiation protocols, SIP lines, are initiated instead of the So then yes, it's cheaper to have those SIP lines, and SIP line is a bandwidth on the internet. The bandwidth would be having certain type of bandwidth reserved in order to be able to carry voice with certain quality. Now, some of the VoIP connections are better than others. That's because some companies would probably try to cut the bandwidth, so you just get enough bandwidth to carry on the human voice so you could understand what somebody is saying. So that's why sometimes you would have some connections with better voice quality and some with a little bit less than good. Right? It depends on who you get and what connection you're actually establishing. Right? So that's the idea of VoIP. Now, internet down, a little bit of a funny thing, so you might want to click that and have a couple of laughs. What happens when internet goes down? Now here's a couple of videos I'm going to ask you to watch. One is 3 minutes and 24 seconds. The other one is 2 minutes and 52 seconds. Right? But this presentation I made way before I created those instructional videos for the labs. However, the more the merrier. You watch this, you watch my videos, and it's just going to bring you that much closer to success. Yeah, there we go. All right. References. Okay, so that's as far as finishing up the last part. And let me just queue up the other class that we have here. All right. So now we're going to talk about topology. Topology, Control L, I think it is. Yeah, full screen. All right. We talked about network types, types of network. Now we're going to talk about how actually networks are connected physically and or logically together. There are different ways of symbolizing the network topology. So for the most part, we're just going to concentrate on 1, 2, 3, 4 basic types, and the other are, well, form of the 4. So this is the basics, and that's the combination or maybe some different representation of or mixing things up. All right, so we're going to concentrate on ring, star, inline, and or chain, and the bus topology. Now let's get some of the definitions out of the way. Definitions. Network topology is the arrangement of a network, including its nodes and connecting lines. What are nodes? We're going to talk about that. Now, there are 2 ways of defining network geometry. Right? So topology and geometry we're talking about here. Physical topology and a logical or signal topology. So topology would be the physical sort of like type of a connection, and geometry would be ways of looking at it. All right, that's as far as I can just put in simple terms. All right, basic elements of a network presentation. Right. Hosts or nodes and connecting links. On one side, we have hosts or nodes. So nodes or hosts are smart devices, anything that connects to the network. Could be a PC, could be a IP camera, internet protocol camera. It could be a VoIP telephone. It could be wireless access point, climate control device, whatever connects to the network and communicates with the network. So the nodes could be computers, wireless access points, routers, switches, hubs, bridges, gateways, whatnot. See, these are 3 dots. That means that, and so on. Printers, and other devices such as IP cameras. Right now, those are connected with connecting links, and they would be copper, fiber, or air. Well, there you go. Now, let's jump into the some of the details or some of the topologies. Ring. Well, it looks like a ring. So these would be the nodes here. All right, for example. This is the symbol of a ring topology, and these would be connecting links, whichever they are, whatever these are, and whatever these are. This could be a computer, like a PC. This could be telephone, VoIP telephone. This could be something else. For the most part, let's just for the simplicity, we're just gonna say, okay, these are the PCs. So each PC is connected, well, either through air or through fiber or through copper. Let's say just Ethernet copper lines. All right. Each node or host connects to 2 adjacent nodes in a continuous pathway for signals through each node. Well, just each one connects to one. There's one on the left and one on the right. All right. It's just like if we form a circle and we each hold hands and we're just singing, I don't know, Kumbaya or something. All right. Now, data travels from node to node with each node along the way, handling every data packet. Let me read that again because I kind of stumbled. Data travels from node to node with each node along the way, handling every data packet. So now here, every node acts as a repeater. Right? So if this PC wants to communicate to this PC, well, it can't just shout across because it's not going to be heard because there's no connecting link. So it first is going to try to send the message in a way that gets to this PC. So send the message along the way. This one gets it. Is it for me? Nope. That's not my name. That's not my address. I'm going to repeat that and pass it along. Okay, this one gets it. Same thing. And this one gets it. Oh, that's for me. All right. And whatever the message is. And if the message needs some sort of a response, then this one is going to respond and continue here until it gets to that. So that's, basically the whole communication is just like a beehive is buzzing, right? Okay, so here's the ring topology. Right. All right, ring topology hardware. Well, laptops or cell phones or tablets or PCs, they do have NICs. Now they look each different because obviously this would not be a network interface card, network interface card that you would find in your cell phone. But I just put those two as examples because they're big enough to present. Right? So NIC, network interface card. Here's a single port. Here's a double port. Which NIC would be used in a ring network? Single port or two port? NIC is the network interface card. Of course, double port. We get this. All right, cool. Yes, double port. For the most part, right? Because you need to connect. You have two connections to each node, so you have to have two connections. And that would be for the physical topology or physical geometry. Is it possible to use single port in the ring topology? Well, technically, yes, and I'm going to show you some very hypothetical situation in which you could, if you're really stubborn, if you want to accomplish that, yes, you could do that. But the point of me showing that would be just to give you a better understanding of what the signal or logical topology would be, how it would be different from physical. So physical topology or logical or signal topology. Okay. All right, so this will be something that visualize the data communication between the nodes or PCs here in this case, when we're talking about the ring topology. That will be that's a visual and a half. All right. Now, you would have, pretty much you would have heard in the past terminology such as ring. Things are connected in ring, or things are connected in a token ring. I'm pretty sure you have heard things that are called token ring. Okay. All right. In a ring, data travels only one way. Let's forget this link. Let's say a couple, few buildings connected together in some sort of way. All right. And let's forget this link right here. Let's say they're just connecting in this way. If the data traveled only one way, and let's say this building wants to communicate with this building, and the data travels only one way. So this building would send the data to this one here, then that one here, then this one, and then this one would get it. Right? But what happens if something happens to this building? The power goes off, network goes down, whatnot. Well, then in this case, this building can communicate with only this building. And that's it. That one will have to wait until the power is restored in this one here. Well, if you wanted to communicate the other way, yes, you could, but it would be considered, the communication would be considered as a token ring configuration. So if a token ring enables data to travel both ways, either way, not both ways, either way, right? So if there's a token ring configuration, if this building power goes off, then this here tries to communicate to that. This one tries to go, oh no, there's no communication here. Okay, well then there will be no response, dead end link. All right. So then it says, okay, well, if I can't communicate this way, I'm going to try the other way. Maybe I can get through this building the other way. So it communicates that. Okay, so there you go. Data can communicate both ways. Ring, one way only. Token ring, things can communicate both ways. Right? Why is it that not everybody? Why can't we just have everybody to use token ring? Well, probably because the ring was developed earlier than the token ring was. Right? That's my guess. If someone can watch this video and have any other ideas, I would welcome the explanation. But both exist. Right? Now, applications. Well, not all the communication happens between just the PCs. There's more to networks than just the PC communication between the PCs, right? Or PCs versus wireless access point or cell phones and tablets for entertainment purposes, or maybe even for educational. There's so much more when it comes to communication between devices. Here's one of the examples, right? Here's a switch. Forget about the switch just 2, 3, and 4. There's a LAN room that has a switch, and the switch is capable of connecting 24 ports. It's a 24-port switch. Switch is a traffic controller. In the simplest term, it will be a traffic controller for the signals and the data in the whole network. So what happens? There's a PC right here. The wire home runs to the LAN room, and that connection from the jack in the wall is just a clean, dry connection to the other jack, which is in something that's called a patch panel. And patch panel is, instead of mounting the jacks in the faceplate on the wall or a desktop somewhere, well, we're going to have many jacks coming from all over the place. If we had that faceplate, we would just run out the room pretty quick, especially if you use like 600 or 800 connections. Wow, you need a big, huge room. So in order to conserve space and to make sense out of things, the jacks are being put in frames right beside each other, conserve space. So that's the patch panel. From the patch panel, in order for that computer or a PC to connect to the network, well, there has to be connection between that PC into the jack in the wall. Then through that, there's a connection to the patch panel, and then from patch panel, one-to-one, each PC is connected to port in the switch. Everything has designated port in the switch. So if there's a 24-port switch, this network would be capable of 24 devices, either 24 computers, or maybe 23 computers and one wireless access point, or whatnot. Anything that connects to the network, it would be able to connect no more than 24 ports. Well, what if you have a company, and the company has, let's say, 97 computers, plus all the other things? You would need more switches. Well, more switch, and if there is no switch that, well, maybe there is, it'll be more expensive. So what's available on the market, there are only 24 port switches, for example. You live in that part of the world, in that town, that they only have those in stores, right? Joke, right? So if you want more, you just add switches. Here's 24 port, add another switch, you have another 24 ports, and you just can keep adding them, and you're going to have to connect those switches in a way that they would act as one big switch. So those switches would have ports to connect, so they can communicate with each other. And look, in a ring configuration, there's a closed loop. This one connects to here, this one connects to here, this one connects to here, and this one connects to here. So there's like one huge ring, kind of a data communication between these switches. So all those 4 switches can function as one common big switch, and you can keep adding those. All right. I'm going to ask you to press that once you download this thing. Later on, I'm going to post it, because I want you to know the difference between a hub and a switch and a router. So there's a beautiful explanation. 7.5 minutes out of your life. Please watch that. All right. Now, here's another video, just a little time, kind of like a real life example of how things are being connected in real life. And I'm going to ask you to watch just right up to 1 minute and 42 seconds. So very short thing. Later on, he explains how to configure those things, and it's kind of irrelevant to us at this point. All right. Move on to something that's called a star topology. It looks like a star, right? What do we have here? Each node or host of a network is attached to a central node. So here's a central node, and everything comes to here. We can also say that all the links or the connecting links home run to a central location. Right? So what do we have here? Each node or host of a network is attached to one central node. The central node is usually a hub or a switch. That's why I'm going to ask you to know the difference between these two. Then the central node can also be another proprietary device, not necessarily a switch. It could be an NVR, which stands for Network Video Recorder, or DVR. Those terms are being used exchangeably. So first, there would be TDR, which is time domain recorder for the video surveillance cameras systems, and that would be the TDR will be time domain recorder, will be just a glorified VHS machine that would utilize VHS tape in order to, and they will have to replace those tapes every morning or twice a day, whatever. Right? Then DVRs came along, which is digital video recorders, which means that the data, instead of being recorded on VHS tapes, the data from the cameras will be recorded on a hard drive. So DVR, digital video recorder. Then those things were networkable, so then the terminology is stuck with NVR, which stands for Network Video Recorder. There are no just DVRs anymore. However, sometimes you're going to hear a lot the DVR and NVR used interchangeably, but now you know just a little bit of a so-called, if you will, etymology of things. All right, so the central node can, so not only a server or a switch, but there could be other devices. And here's an example of that. All right, star topology is the most common physical wiring configuration, considering, okay, I keep throwing those terms at you. Horizontal network wiring. Okay, so the star topology, we know what it is. Everything home runs to central location is the most common one. That's when installing networks, that pretty much is being done, period, right? Considering horizontal network wiring, keep that in the back of your mind, because we're going to tackle that very soon. Star topology, there will be a concept, kind of a drawing rather than diagram, but you know what I mean. Here's the nodes, PCs in this case, and they all go. The concept is that they all connected to the switch, and the switch controls the traffic between the whole thing. Now, in reality, that's what it looks like. Right, these will be the patch panels, and will be the rear side of the patch panels that are in the equipment racks. Every wire, every single wire that is connected here goes somewhere to a single type of a jack that goes underneath the desk, on top of the desk, in the ceiling, on the wall, wherever the smart device has to be. Notice those wires are being bound by Velcro instead of zip ties. Here's a bit of a zip tie thing going on. That's an older system. Now here is that looks like, well, that looks like the old Cat5, not even Cat5e system, although it could be Cat5e. Well, is that zip ties, or maybe it is Velcro that's being used? Yeah. Now these look like newer wires. These look to me as Cat6 at least wires. They're a little bit thicker. Now Velcro is being used, so the wires are not being deformed. If you have zip ties and you squish them, you're deforming a wire at that spot. And if you do that, you're changing the physical properties of the cable, which means you're changing the specifications of the cable. They are that sensitive. So that will be the rear side of that. And this will be the front side of the equipment rack, where all those wires here go to the switch. Sorry, go to the patch panel. And from the patch panel, they're being patched through to a switch. So let's say those yellow patch cables are connecting its individual ports from the patch panel right to the ports on the switch on one-to-one basis. All right. Now, remember I was talking to you about horizontal wiring. This is how modern buildings are being built right now, especially the commercial high-rises, Toronto downtown, New York downtown, whatnot, anywhere downtown. Commercial business high-rises are constructed in a way, or other buildings as well, hospitals, schools, quite often, that the communication closets are in the same sort of spot everywhere. So you could just run wiring from top to bottom, from bottom to top, and it is much easier that way. It is much easier that way to run the wires that can be routed to anywhere that we need in that building. So this vertical run here, it's called a riser. Right? Now over here we have something called main cross connect. Sometimes it's called a demarcation point. Demarcation point is a point of entry. Sometimes it's called demarc point, or sometimes you're just going to hear, where's the demarc, right? So that's point of entry. So that's where all the wires from the city side are coming into the main cross connect. There could be a secondary cross connect. They could be branching off, right? But for the simplicity purposes, this is just shown like that. So then it goes to the intermediate cross connect closets or frames. Excuse me. This riser also will be called a backbone for the whole structure. Okay. Now, this one or either of those communication closets could be considered as a backbone for a local area network. So this will be the backbone of things. And then here will be the horizontal runs. Horizontal runs are the runs that home run to a specific location. So if there's a communication closet for this floor, for this business that occupies that floor, now those business high rises are so huge that sometimes the floors are being divided so you can have 4 or 5 different businesses just on one floor. Those high rises don't look like much from outside, but once you get there and you go inside, yeah, there's a lot of area there, a lot of real estate to cover. So let's say, but for the sake of argument here, we're going to have that one floor is occupied by one business. And you're going to connect all the jacks to that one location there, and that will be considered a horizontal run. Now, mind you, if, let's say, this PC in the middle goes here and comes down and is connected to this closet, then that one PC would be part of the horizontal run of like this one here. So these will be horizontal runs, that home run to one location. And this will be the riser. Right? And that's also considered a backbone or different backbones to that would service a specific LAN local area network. So here's as far as terminology here. Now, structured cable network, that's what star topology would look like. Another visual. Here a bunch of wall jacks, and the wall jacks all home run to that central location. See if I can zoom in here. They all run to the central location here. This would be the patch panel, or many patch panels connected, put together physically in the same rack, equipment rack. And from there, patch cords are being used to connect each and individual run to a specific port. So let's say this is the PC, it's connected to the wall jack, then through the wiring, the horizontal run or home run goes to, let's say, this one here, this first port on the top row, and then from there it's being patched right to a specific port of the switch. And every other computer is connected that way. When it comes to installing networks or laying down infrastructures, routing wires in the walls, through the walls, in the ceilings, and all that stuff, that's probably the bread and butter of this business. And doing it properly, doing proper terminations, doing it fast and efficient, and then at the end you test and troubleshoot to see what else, maybe you make kind of mistakes. If you're connecting and terminating 800 jacks, which means like 600 jacks, because 800 runs would have a jack on one side and jack on the other side. So if you have 800 computers or 800 wall jacks, that means you're terminating 1600. Of course, sometimes your brain might play some tricks on it. And by mistake, you can reverse a couple of pairs or something. So at the end, you're just doing testing and troubleshooting, and maybe fixing some things something that happened, and then running the tests, saving the tests, and presenting it to the client. And sometimes the client requires something that's called a certification. So if you want, in order to certify a line, you're going to have to connect a very expensive tester, expensive tester, in the range of the one that we have there. It's I think costs about anywhere between $6,000 and $12,000. depending on what kind of attachments you're getting for that. So you can get attachment for copper, for Ethernet, for coaxial cables, for fiber optics, and all that stuff. So there's the main brain of the tester, and that tester, the certifier, goes through some rigorous tests and does some more rigorous frequency response and whatnot in order to certify a run as such. Like, for example, Cat5e, Cat6, Cat6a, Cat7, or so on. Right? And all those have certain specifications, and we're going to talk about those too in some further lectures. Right? So that's the most popular activity that will be, that will be done. Pulling wires, installing wires, terminating, testing, troubleshooting. Also, what else is mounting the equipment, setting up the racks, mounting equipment in the ceilings, in the walls, and doing service calls and troubleshooting, and maybe replacing and troubleshooting some stuff in there. So that's the bread and butter of the business. Right? Okay, well, zoom out so I can switch. Now, moving on to something's called a bus topology. Right? Now, what do I have here? Bus topology was used in LAN settings until early 1990s, so probably before most of you were born. Now, presently, I have to change this year. Presently, all LAN horizontal systems are wired in a star configuration. What it used to be is there will be a PC, and so on. And there will be a coaxial cable just run past every PC, and there will be those taps. You would tap into the coaxial cable, so you would just let the signal pass through, and you would tap in with another wire here through the PC. So everything would be just running on that one coaxial cable. So the data wasn't that fast to be able to, as far as the ability to move. However, early 1990s, 1990, 1991, 92, that's when there was no internet available to public. Internet became, internet existed for a long time before that. However, it was not available to public in the way that it is now. So basically, as far as we're concerned, it did not exist. It existed, but not to us. Then, so in that case, the network, it just needed some sort of data transfer abilities from one PC to another, but there was no videos being played, no audio being played. Maybe you would need to connect some devices like a common printer for the office or so or whatnot. So the speed was not that important. Well, speed is always important, but it was not that crucial at that time. So then the bus system, it would look like this here. There was one main connection, and everything taps in. Remember when we were talking about the PA system, when you have one main speaker line and all the speakers are connecting to that one line through the step down transformers and using a step up transformer for that. So the lectures that we had before, that would be sort of a primitive way of describing a bus, but not exactly. But you gotta start somewhere on that kind of stuff, right? Now, there's a certain bus topology that spans over a huge area. Well, sometimes actually it can span over the whole planet. It's called radio. You're driving your car to your work or to school or wherever you're driving, and you decide to turn on the radio. Well, all the electromagnetic waves are in that one link in the air. It's all in the air at the same time, in the same space, all the frequencies from different radio stations. But with that one radio in your car, you're tuning on into a specific radio station that transmits specific radio waves within the whole big pipeline of what's called a bus. So that's one way of understanding it. Right? Another way of understanding it. All right. Another way of understanding bus topology is also, again, it's a primitive way of showing it, but something that we can understand easily. Let's say fire alarm. Here is one zone of a fire alarm. What is a zone? A zone is a connecting point that connects a sensor or a bunch of sensors. Now, in the fire alarm, all the devices, there could be smoke detectors, heat detectors, pull stations, and some other devices that would alert certain conditions. In the loop, here's the loop. It goes from here to here and comes back here with all those devices that are in the open position. So they have a physical switch or a relay that makes things open. So as far as these 2 points, these devices do not exist at the idle state. It just doesn't see because the open switches here. Now, if let's say this would be a zone that couple of trigger points, like one trigger point with couple terminals, that would service the hallway, on the floor 3 north hallway or something like that. It could be labeled as that. There could be another zone that services something else, another zone that services maybe the furnace room or something like that, and whatnot. So there are the zones. The zone will have to see something that's called an end-of-line resistor with a specified resistance that it's actually looking for, quite often 4.7 kilo ohms. And it has to be mounted at the end of the line. If that zone sees that resistor, that resistance, then it knows that the line is intact. There's no any breaks. If there's a break in the line, it's going to sense, this zone is going to sense it, and it's going to go into a trouble condition. Trouble means that's not alarm. It means that this sensor might not sense things if something happens because there's a trouble on the line. The line is broken. Right? So then, there's a service call to find out where, what happens, what's going on. All right, now, if one of the devices triggers, let's say this is a smoke detector, and there's a smoke nearby, and the smoke detector is going to sense that smoke, boom, it's going to close the switch, and it's going to cause a dead short right here. So this is going to sense that, no, I am not seeing 4.7 kilo ohms, I'm seeing a dead short on the line. Oh, one of the sensors has triggered, boom, I'm going to go into the alarm state. All right, so that's one way of bus, primitive way of having a bus. Now here's a little bit more sophisticated way. Security alarms. Let me just zoom it properly. All right, on the main board of a security alarm, most of the security alarms, you would have zones, the common and the zones would be the common, and it will be zone 1, the common, zone 2, and so on. Right? So security alarm works in a similar way. So there'll be the zones for the sensors, but let's not talk about that. Let's talk about the bus. What do we have? Oh, look, we have connections, 4 connections. Auxiliary power, plus and minus, usually will be 12 volts to power up devices. And I just didn't draw the wires. The security alarms usually use something that's called a quad wire. It's a straight wire, 24 gauge, 22 gauge most of the time. And it has 4 colors, red, black, yellow, and green. And usually red and black are reserved for the power. So one quad wire would just go from one keyboard to another keyboard, forming a bus. All the keypads are tapping in to the same bus line. See that? Here, they are sharing the same bus line. And through this bus line, those keypads would communicate with the main board on the same way as radio would work, except we're not using the waves, electromagnetic waves that travel through air, but we're using some different signal protocols that can utilize the same pair, one common pair. So that, it's not a PC, it's not, but bus is commonly used in more than one place. All right. Let's move on to something that's called a inline or chain topology. Here's a symbol for that. Here's a symbol for inline or chain topology. Let's just do the analogy of the switches. Before we do that, let's go to some definition. In this configuration, nodes are connected to each other through each other in a chain configuration. Each node acts as a repeater. As opposed to a ring configuration, the last device is not connected to the first device to form a looped pathway. So this will be the chain topology. They're just connected in a chain. Where can you find those? Quite often in an industry, when there are those control modules that are controlling certain machines, and they are just being connected from one machine to another in a chain topology. Now, the difference between these switches here, switch assemblies, here's 4 switches and here are 4 switches. These 4 switches are connected in a ring topology. See, there's a kind of closed loop here. And these 4 switches are connected in a chain topology. Of course, this will be the more efficient one because, well, if there is a broken link here somewhere, then this switch will not be able to communicate to that. Right? Excuse me. So that's just to show you the differences between. And I'm going to give you some questions on the test. I'm going to redraw this a little bit different. So you're going to have to actually closely analyze things. I'm going to, is it chain or is it ring topology? So there you go. Hand, wink, wink. Yeah, okay. As long as you understand, learn, I'm happy. Now, inline chain topology, I'm going to give you a couple of, before I let you go, I'm going to give you a couple of real life situations with real life equipment that I want you to start getting familiar with, just so if somebody talks to you about mounting certain type of device or installing certain type of device or servicing certain type of device, you're not going to ask them, what is it? Well, yes, there are going to be certain things that are new on the market, or else even I am going to, okay, what is it? But you're going to ask less and less. All right, simple, real life situation. Workstation and printer connected in a star topology because all those devices home run to a central location. So these two are being connected in a star topology. Well, here, these two are connected in an inline topology. See? This would be an example of like a common printer for the whole office or a personal printer for that specific workstation. The point is, here's a star configuration, and here is an inline configuration. Let's move on to something else. All right. A real life example. Ethernet extender. This Ethernet extender is connected in inline. Is connected inline with the Ethernet link. Well, the Ethernet link goes from the switch to the PC. Here's the challenge. Ethernet links are not usually, well, forget the word usually. They can't be longer than 300 feet. And some of them can't be longer than even a shorter type of distance, like 180 feet, 140 feet, depending on what you want to accomplish and what type of wiring you're using. But the most you can get is 300 feet. It's actually 328 feet, but we are reserving that 28 feet for patch cords and things. So we're not installing anything that's longer than 300 feet. Excuse me. So what if that one PC workstation is the length of the wire that's connecting that to the switch is longer than 328 feet? It's just physically it's in that spot, and that's it. Well, if that's the case, then if you connect a straight as a link, Ethernet link, you're going to have communication that is intermittent. Sometimes it works, sometimes it doesn't work. Unexpected data loss, losing data packets, and so on. Well, what do? Well, somewhere in between, we can install something that's called an Ethernet extender. The Ethernet extender can get its power because it's a smart device, active device. It can be connected to a power supply and plugged into the wall, power supply connection, or it can get its power from something that's called a PoE, power over Ethernet, that is available in the switch ports. Not all switches have ports that are capable of PoE, depending on the price and the specifications of many different kinds of switches. So some of the more expensive switches have the PoE capability on every port, which means every port is capable of sending and receiving signals, data signals, acts as an Ethernet link, but also it has superimposed on some of the pins or some of the prongs, has superimposed a voltage that can power up equipment. So that can be powered up by that if the switch has those ports capable of that. Some of the switches have all the ports capable of PoE. Some of the switches have no PoE capability on any of the ports, and some of the switches would be kind of economical. By saying that, I mean maybe it's like, okay, the first 8 ports are PoE capable, and the other ones are just signal. So you gotta watch what you're buying, and when you're specifying things and you're running specs or designing a system, you gotta pay attention to that kind of stuff. So in order to establish solid communication, I don't want to use the word reliable, because the word reliable is for certain type of communication, reliable transmission and unreliable transmission, and that has nothing to do with being good or bad, right? But I'm talking about good or bad here. There's a bad connection, there's a good connection. Bad connection with intermittent or maybe not working at all, and you want to have a good connection that all the signals are traveling properly and it can be received, and this thing can be dependable, okay? Communication link. So yes, it would just put somewhere in the middle, install the Ethernet extender, so the distance between here and here is less than 300 feet, and the distance between here and here is less than 300 feet, and you're good. You're not going to get as much speed as you want, maybe in some cases, but sometimes the speed is not crucial. Like, for example, if this is a cash register, which is a workstation, it's a PC, a cash register is not going to require high-speed communication. It just transmits transactions, shoots down some numbers. Speed is not that important, but the reliability of the communication is important, right? So there you go. Ethernet extender. There are devices like that. Now, another one, PoE injector. Let's say you have a switch that is not capable of any PoE. Somebody bought it, wanted to save some money. All right, we don't need PoE. Here's my favorite line from some clients. We won't ever need anything more than that. All right, I'll leave that alone. Okay, so, but somebody purchased that, and 2 years from now, they decided, I know, we could use wireless access points, for the Wi-Fi because clients are asking, All right, well, okay, so that wireless access point is going to live in the ceiling, one of the ceiling tiles, and there's no power outlet to plug in the power transformer or the power supply, so you can power up that wireless access point. You can call an electrician, or you could be an electrician, to install there, but well, not a very efficient way of doing things. What you can do is you can put something that's called a PoE injector. So that would go right in the equipment rack, right beside it. And usually there's all kinds of outlets there because things are being plugged in anyways. So power has to be available. And so you plug that thing right into the outlet to provide the power for that. And you will plug in the Ethernet cable into one of the ports here. And then from that, plug into there. So up to here is just a signal. The power is being injected on some of the pins and superimposed on the wire. So this cable carries the signal and the power. So all you have to do is plug that in, and this device is being powered and is communicating with that. So PoE, power over Ethernet, those devices exist. All right. Last example. Voice over IP, telephony. Quite often you're going to see, especially in retail environment, or in some offices set up as well. Here's a VoIP telephone, or sometimes they're called IP phones. It plugs in to a network. It's just like a network node. And a lot of those phones have input and output. In order to add the phone, you unplug the PC from the data outlet, and you plug in the phone, and from the phone, you continue to the PC. The phone is going to grab the phone signal out of that Ethernet connection, and the PC is going to grab the PC information that it needs for the Ethernet, and each is going to work as two independent devices through one link. So, inline topology. This phone is VoIP telephone set is connected in line with the workstation computer. There you go. Is that the? Oh no, that's not the thing here. All right, one last thing, I promise. All right, here we have some that's packet tracer. You might want to install that, and there's all kinds of information if you want to practice being IT person. Pretty good. It's called packet tracer. Right. So I just use that just to kind of draw things for the purpose of this presentation. Here's a switch, and here a bunch of PCs connected in a star configuration, and then inline, here's the router, and here's the Ethernet connection. So, are these PCs connected to the switch in a ring configuration, or is the star? Well, physically it is a star, and it will be a star. Now, can the system work as a ring? And if so, then how? Now, this is the highly hypothetical situation that I told you I was going to give you. It is just to show you the difference between the physical topology and the logical or signal topology. You are not going to deal with that kind of stuff. This is a highly hypothetical situation just to help you visualize between the two. All right, I'm going to show you how. Let's see here. Here's a switch, and it has a bunch of PCs connected to it, each to individual port, designated port. Now, physically, it's a star topology. Logically, it can be a star or it can be a ring, depending on the switch configuration, how you configure the switch inside. Then it could act as a star system, or it could act as a ring, and it would transfer the data in such a way like this here. And that's when we can use, you could use that single port network interface card. You're not going to deal with situations like that. You're not going to come across situations like that. It's just to visualize the differences between the physical and logical topology. Now, the lab foundation, I don't care much about. You can look at this thing here. This here, IDC connection. I'll explain that to you, but here's the idea. IDC, insulation displacement connection. Here's the connector that's right in every one of those those grooves here. There's one of those in some way or form. Now, how do you make an IDC connection, insulation displacement connection? You put that wire on top of that connector, and you use some kind of a punch down tool to shove that thing in. And this connector is going to bite into the insulation, puncture it, and make contact with the copper that's inside the jacketing, displacing the insulation, making connection with the wire, with the conductor. That's why it's called IDC, insulation displacement connection. One thing I'm going to point out to you, I got this thing from the internet, this picture, here's a reference from that. And somebody used, and I was thinking about replacing that because this is a, well, I want to call it a mistake, but this is a bad scenario. It is presented with a stranded wire, not a solid core wire. Insulation displacement connection does not like stranded wire, simply because when you push that thing and those connection, those blades of the connector bite into that, they can actually cut some strands. So this is meant for a solid core wire, just so you know. And I left it there so I could talk about it. Okay. All right, that's it for today's lesson. And if there are any questions, please shoot or go online or go on voice. If not, I'm going to ask you to do me a favor and enjoy your weekend. All right. And today is a special day because it's not almost Friday. Today is Friday. All right. Stay healthy and safe, and I'll see you when I see you. Thank you very much, guys. Hey. All right.